We can determine the electric field of a distribution of electric charge by summing the contributions from tiny bits of electric charge in the distribution. In the limit that these bits of electric charge are infinitesimally small, this summation becomes an integration. For example, let's calculate the electric field of a uniformly charged disk, a distance z away from the center of the disk, along the longitudinal axis of the disk. We can model this disk as a collection of thin rings. This shape is convenient not only because it matches the geometry of the disk, but also because we have already solved the equation for the electric field of a ring. In this equation, the z-axis is perpendicular to the plane of the ring, with a positive direction pointing away from the ring. In the limit that these rings are infinitesimally thin, we can express their contributions to the electric field of the disk using the following equation. In this equation, dq is the electric charge of each infinitesimal ring, and r is the radius of each ring. The variable z is the distance from the center of each ring to the position where the electric field is measured. This distance is the same for all of the rings, since each ring lies in the same plane. This is another reason why it is convenient to use thin rings to model the disk. Since the disk is a two-dimensional object, we can express each infinitesimal bit of electric charge in a ring as the product of the electric charge density of the disk, denoted by sigma, and the infinitesimal surface area of the ring, given by 2 pi r dr. The electric field of the disk is the integration of the contributions from each ring. The limits of this integration are the radii of possible rings within the disk, and thus are from 0 to the radius of the disk, denoted by capital R. Since the disk is uniformly charged, its electric charge density is a constant and can be taken outside the integral. Similarly, the variables z and epsilon naught, as well as the z hat unit vector, are also constants. The remaining integration is straightforward. We arrive at our final equation by substituting for the electric charge density of the disk. As expected, if the electric charge of the disk is positive, the electric field points along the positive z-axis. In other words, if the electric charge of the disk is positive, the electric field points away from the disk. Similarly, if the electric charge is negative, the electric field points towards the disk. Next, let's calculate the electric field of a uniformly charged solid cylinder, a distance y away from the top of the cylinder along the longitudinal axis of the cylinder. We can model the cylinder as a collection of thin disks. This shape is convenient not only because it matches the geometry of the cylinder, but also because we have already solved the equation for the electric field of a disk. In this equation, the z-axis is perpendicular to the plane of the disk, with a positive direction pointing away from the disk. In the limit that these disks are infinitesimally thin, we can express their contributions to the electric field of the cylinder using the following equation. In this equation, dq is the electric charge of each infinitesimal disk, and capital R is the radius of each disk. The variable z is the distance from the center of each disk to the position where the electric field is measured. Since the cylinder is a three-dimensional object, we can relate the infinitesimal bit of electric charge in each disk to the infinitesimal volume of each disk using the volume electric charge density of the cylinder. The electric field of the cylinder is the integration of the electric field of each disk in the cylinder. The limits of this integration are from y to y plus h. In other words, the closest that any disk in the cylinder can be to the position P is y. The farthest any disk in the cylinder can be to the position P is y plus h. Since the cylinder is uniformly charged, the electric charge density is constant and can be taken outside the integral, along with the other constants. This integration is straightforward and gives us this equation. We arrive at the final equation by substituting the expression for the electric charge density of the cylinder. As expected, if the electric charge of the cylinder is positive, the electric field of the cylinder points away from the cylinder. And if the electric charge of the cylinder is negative, the electric field of the cylinder points towards the cylinder.